Okay, so for this video we're going to be doing area between two curves and arc length. So we'll start with area between curves. Let's say you have two functions, f of x and g of x, and I'll label f of x in red and g of x in blue. So if you have two functions, and let's say you have f of x that's graphed right there and on the interval a to b, and then you have the area. If you wanted to find the area of f of x under the curve, you would integrate it from a to b of f of x dx, and you would get this shaded region right here. So this whole shaded region underneath of f of x is what you would get. So then let's say you have a second curve, g of x. And g of x is this blue curve right here. So if you wanted to find area underneath the g of x curve, the integral from a to b of g of x is what you would evaluate, right? Okay, and that would give you this area right here, the area underneath this curve. So the area, the blue shaded area is the area under g of x, the red shaded area is the area under f of x. So let's say I wanted to find the area between the two curves. Just let's say I wanted to find the area between f of x and g of x. So all I would do if I wanted to find the area between the curves is take the red area of f of x and maybe just subtract the area that I found from g of x. So the integral from a to b of f of x dx minus the integral from a to b of g of x dx. Now by properties of integrals, if you have two integrals and you're evaluating it on the same interval, you can just do one big integral of a to b of f of x minus g of x. Okay? So this applies no matter what quadrant f of x and g of x are in. As long as you do the top curve, the integral of the top curve minus the integral of the bottom curve, you're going to get a correct answer either way. The pluses and minuses work each other out as you're evaluating the integral, so you don't have to worry about what quadrant am I in, which ones should be positive, which one should be negative. Everything is worked out mathematically on its own. You just have to do the integral of the top minus the integral of the bottom. So, the same works if you have two functions in terms of y. So let's say I had h of y, and I wanted to find the area between the two curves of h of y and another function. Well, I can integrate with respect to y, and that would give me the orange shaded region. And I can integrate j of y with respect to y, and that would give me the green shaded region. Okay, so if I wanted to find the area between the two curves, that black area right there, I can do the same thing. I can do everything with respect to y this time. So my boundaries of my integral are going to be on the y-axis. The area between the two curves h of y and j of y is going to be the integral from c to d this time of h of y minus j of y dy. Okay? Alright, so let's try a few examples. First, find the region bounded by the graphs of y equals x squared plus x, y equals negative x equals 0, and x equals 1. The two graphs I have already sketched there for you. Sometimes you'll have to sketch it on its own, so that's why it's important for you to understand the shape of the graph and how to graph parabolas, lines, and things of that nature. But x equals 0 and x equals 1 is not graphed, so I'm going to just put vertical lines at 0 and 1. And that's the shaded region that I want to find the area between the two curves. Okay, so I'm trying to find this gray area right here. So I am just going to do it, they're all in terms of x, so I'm going to do the integral from 0 to 1 of my top curve minus my bottom curve. And it's all in terms of x, so it's dx. The integral from 0 to 1, my top curve is the parabola, so it's x squared plus x plus 2, minus my bottom curve, which is just x dx. I'll simplify the integral, make it x squared plus 2x plus 2 dx. Integrate that, which is x cubed over 3 plus 2x squared over 2 plus 2x, evaluated from 0 to 1. Plugging 1 in. I should plug in 0. Don't forget to plug in 0 too, because a lot of times people automatically assume that 0 plugged in will be 0, and it's not always the case, so you want to make sure that you plug 0 in. So, I get 10/3 for the answer to example 1. So you'll just need to remember to do top minus bottom, and if the bottom term is in terms of more than one term, then make sure you distribute that negative across the bottom function. Example 2. Find the region bounded by the graphs y equals 6 minus x squared and y equals x. Sketch it. So I sketched it there for you, and to integrate it we have to find the intersections. Now normally you wouldn't have the graph, so let's pretend that you don't have the graph, and you would have to find the intersections of the two functions. So we would set 6 minus x squared equal to x and solve for x. Bring everything over to one side, factor it out, and I'll get two intersections, two x value intersections, -3 and 2. So if you look at the graph, you'll see that -3 and 2 are the two x intersections for the two functions. I'm still going to integrate top minus bottom for this function because it's easy. I always have the same top function minus the same bottom function, so if I always integrate top minus bottom, then we'll be okay. So you have the integral from -3 to 2 of 6 minus x squared minus x dx. Just do the straight math, -3 to 2, simplify it, -x squared plus or minus x plus 6, integrate it, -x cubed over 3 plus x squared, or minus x squared over 2 plus 6x, evaluated from -3 to 2, you get 125 over 6. So that's how you do that one. Most of the things you already know, it's just the area between the two curves is top curve minus bottom curve. So let's do another example. So let's say we have this one, find the inner region bounded by the graphs x equals 0 in the first intersection. So I set sine x equal to cosine x equals pi over 4. That's where I know I have to integrate from 0 to pi over 4 of cosine x minus sine x dx. So sine x plus cosine x is my antiderivative. Plug in pi over 4, and I will simplify. Notice how I plugged in 0, and the second function, when 0 was plugged in, was not 0, so make sure you plug in 0. Alright, so square root 2 minus 1 is our answer for that one. Now notice for example 6, x equals 3 minus y squared and x equals y plus 1. If you were to solve for x, you would have a plus or minus function when you square rooted that y. So if you solve for x, you'll have two separate functions and you'll have to do two separate integrals. It's going to be easier if you evaluate this function from right to left. So instead of top minus bottom, we're going to do right function minus left function for this one. And it's all going to be in terms of y. The intersections are very easy to see on this graph. If they weren't easy to see, you would set the two equal to each other and solve. So let's just do that for us to have it in our notes. So set the two equations equal to each other, solve for the y values because I'm integrating from right to left this time. So I got -2 and 1, which was shown on the graph, so we're good. So I'm going to integrate from -2 to 1 of the right curve, the curve on the right, 3 minus y squared, minus the curve on the left, dy. And we just simplify. -y squared minus y minus 2 dy. Integrate that. And get our answer, -7.5. Now, if you are going to integrate past an intersection and the curves change, like for example, in example 3 above, if we wanted to integrate to 1.5, I'd have two separate integrals that I'd have to do because I have a different top for 0 to pi over 4 than I do from pi over 4 to 1.5. So I'd have to do two separate integrals. So make sure that you don't go all the way if your function switches whichever one's on top and whichever one's on bottom. We're not going to do an example today, but we'll do another one in class tomorrow. Okay, so for time's sake for this video, and I know that you took a test last class or you're in between taking a test right now, so just for time's constraint, I'm just going to give you the formula for arc length, and maybe we'll go over how to find it in class if you want to. But here's the formula for arc length. It's just the integral from a to b of square root 1 plus dy dx quantity squared dx. Or the integral from a to b of 1 plus f prime of x quantity squared dx. You can also do arc length with respect to y, so it would be the integral from c to d this time, and c and d are y values of square root 1 plus dx dy squared, or the integral from c to d of 1 plus f prime of y squared dy. Okay, make sure you memorize these formulas. They'll come up again when we do parametrics, but memorize these for now when you're just doing regular arc length because you'll need them. So if you need to pause this and write it down, or if you're just printing out my notes, then do whatever, but it needs to be in your notes, okay? Alright, let's do a couple examples. Okay, so number 1, find the exact length of the curve for y equals 4x from 0 to 3. Verify geometrically. So that's easy. We'll just use the formula, the integral from 0 to 3 of square root 1 plus 4. Okay, now I used 4, remember, because it's the derivative goes into this formula. 1 plus 4 squared dx. Okay, and we'll simplify that. Integral from 0 to 3 of square root 17 dx. Well, the integral of 17 is x root 17, evaluated from 0 to 3, so 3 root 17 minus 0 root 17, so you just get 3 root 17. It says verify geometrically, so let's draw a picture of what 4x looks like. It's just a linear equation that goes through 0, 0. So if I went over 3 units, then I would be going up 12 units, right? So the length of that line is square root 17, or 3 square root 17, which is the answer that we found when doing the arc length formula. So it gives you the same answer, but what if it wasn't a straight line? Then you would have to use the arc length formula. Okay, example 2 is another straight line, but we're just going to use the formula, integral from 0 to 2, square root 1 plus 5 squared dx, integral from 0 to 2 of 26, x root 26, evaluated from 0 to 2, so it's 2 square root 26 minus 0 square root 26, so you get 2 square root 26. Example 3, integral from 0 to 4 of 1 plus, okay, This time I used the derivative of x to the 3/2, which is 3/2 x to the 1/2. Simplify a little bit. Integral from 0 to 4 of 1 minus 9/4 x dx. We're going to have to use u substitution. So u equals 1 plus 9/4 x. du is 9/4 x. I'm going to change my shoes, or the values of my integrand. So it's going to change from 1 to 10. I'll put my 4/9 on the outside. Integral from 1 to 10 of square root u. Integral of square root u is 2/3 u to the 3/2 evaluated from 1 to 10. 8/27 times 10 to the 3/2 minus 8/27 times 1 to the 3/2. Okay, and you can stop there. Remember, you don't have to simplify. At time 0, bug starts crawling along a path. Y equals 1/3 t squared plus 2 to the 3/2. Y in feet, t in seconds. How far does the bug crawl in 2 seconds? Alright, so we're following him on a path. This is like almost like a parametric equation, but we're following him along a path. So you're going to want to do an arc length formula. 0 to 2 of 1 plus dy dt squared with respect to time. Integral from 0 to 2 of 1 plus, okay, the derivative is 1/2 t squared plus 2 to the power of 1/2 times 2t squared dt. And you simplify it to 14/3 feet. I don't have enough room on here to do it. I know you need to integrate this, so if you simplify it, it should come out. You might want to try it on your own, but you get the point. Anyways, that's the end of this video. Don't worry about doing any homework tonight, but we'll do some practice in class tomorrow, and then we've got to get started on volumes by cross-section. And I'll see you tomorrow. Okay, bye.